Aromatic, derived from Latin aroma, meaning fragrance.
Smells nice.
Arenes are aromatic hydrocarbons containing one or more benzene rings.
No, not those
These
rings.
are subgroups of aromatic hydrocarbons.
So that means all arenes are aromatic compounds, but not all aromatic compounds are arenes.
Many scientists were confused about the structure of benzene. Kekule was one of them. He had a dream. The vision of the snake continued until the snake of atoms formed itself into an image of a snake eating its own tail. This dream gave Kekule the idea of a cyclic structure of benzene. Kekule's model suggested that there are two forms of benzene. This is where the carbons are arranged in a hexagon with alternating double and single bonds. Don't eat the carbon! Kekule argued that benzene was in a fast equilibrium, so the approaching Br2 molecule couldn't be attached to the changing double bond. As you can see, the Br2 doesn't react with the benzene molecule that Kekule suggested. Another model had to be suggested.
Where's benzene?
He hasn't been seen.
The problem is that Kekule predicted uneven bond lengths. However, in reality, all bond lengths are the same, approximately 0.139 nanometers. The delocalized electron model for benzene shows the p orbitals on each carbon atom overlapping with the carbons on both sides. Sideways overlap makes pi bonds, which are spread out over the whole ring. The electrons are delocalized because they are now not held between the two carbon atoms, but are spread all over the whole carbon ring. There are 6 delocalized electrons, 2 of which go into each of the 3 molecular orbitals. The delocalization of the electrons means that there aren't alternating double and single bonds like in the Kekule structure.
The original structure of benzene by Kekule was 1,3,5-cyclohexatriene. Benzene is more stable than 1,3,5-cyclohexatriene. The delocalized model of benzene shows the carbon atoms in the ring each form 3 sigma bonds. This uses 3 out of the 4 electrons, which leaves 1 electron from each carbon atom in a 2p orbital, which overlaps, giving the delocalized rings known as the pi system. Experimental data shows that the benzene is planar with bond angles of 120 degrees, which means that it must have sp2 hybridization, so each carbon atom has an unhybridized atomic p orbital with it. The overall sp2 orbitals creates the sigma bond that helps to hold the ring together. The side-to-side overlap of the p orbitals occurs in both directions, which will lead to a complete delocalization in the pi system, therefore great stability to the molecule.
Let's start with the overall equation for the nitration of benzene, which is benzene plus nitric acid gives you nitrobenzene and water. However, there are certain conditions for the reaction to take place. A sulfuric acid catalyst. Here is the electrophilic substitution of benzene. Step 1 is the formation of an electrophile. The nitric acid would react with the sulfuric acid to produce a nitronium ion and water. Okay, so now I'm going to show you the mechanism for the nitration of benzene. Here we have the benzene ring. This represents the delocalized electron cloud. Therefore, the electrons are attracted to the positively charged nitronium ion. The arrow shows the movement of electrons. This would produce an unstable intermediate. Here you can see an incomplete ring of the delocalized electron cloud. This is because over here, 2 electrons have been lost. Now, because this is unstable, in order to stabilize it, there are a movement of electrons from the hydrogen to reform the electron cloud. The overall mechanism for the nitration of benzene. So you've got benzene here, and you've got the movement of electrons from the benzene ring to the nitronium ion to produce an intermediate, and then you've got the movement of electrons from the hydrogen to the benzene ring to produce nitrobenzene plus H2.
The bromination and chlorination of benzene is an electrophilic substitution reaction. This reaction can only occur with a catalyst present, for example, iron. In the bromination of benzene, benzene reacts with iron bromide to form bromobenzene and hydrogen bromide. Iron bromide acts as an halogen carrier, which is a molecule that temporarily bonds to an electrophile, which in this case is a halogen. Iron bromide reacts with bromine to give FeBr4- and a bromine ion. This bromine ion is the electrophile used in the mechanism for the bromination of benzene. Electrons come out of the ring to the bromine. This breaks the circle of delocalized electrons to form a plus charge. Hydrogen gives its electrons back into the ring to form bromobenzene and a H+ ion. This H+ ion can be used to regenerate the catalyst. This is the equation for it. For the chlorination of benzene, the halogen carrier used is aluminium chloride. The same mechanism occurs, but the final product is chlorobenzene and a H+ ion. Benzene is a hugely important compound in organic chemistry. Benzene consists of 6 carbon atoms joined by a ring with a hydrogen atom bonded to each carbon. One or more of these hydrogens can be replaced with a functional group to form a variety of compounds.
Benzene is a carcinogenic.
Chlorobenzene is used as a solvent. Bromobenzene is used in the preparation of pharmaceuticals. Nitrobenzene is used in the preparation of dyes. Phenol is used as an antiseptic. This is the production of paracetamol. I really would explain it, but I'm pretty tired now. I think I've had enough of chemistry for today, and I'm sure you do. You have too. Just leave it on for a while longer so you can have a look. A disclaimer, I'm not here to advertise boots.